Hello, Anjay Swaminarayan to all. Today, for standard 12th science in physics subject, we are going to continue our chapter 3 current electricity. The topics that we are going to cover are 3.13 Kirchhoff's rules, 3.14 Wheatstone Bridge, 3.15 meter bridge, and 3.16 potentiometer. So let's start with our first topic, topic number 3.13 Kirchhoff's rules. Electric circuits generally consist of numbers of resistors and cells, and all these are interconnected sometimes in a complicated way. Means if we want to make a complicated circuit, then these resistors and cells are interconnected in complicated way. The formula we have derived earlier for series and parallel combination of resistors are not always sufficient to define all the currents or determine all the currents and potential differences in the whole circuit. Two rules called Kirchhoff's rules are very useful for analysis of these electric circuits. Given a current, we start by labeling current in each resistors by a symbol say I and a directed arrow to indicate that the current is flowing along the resistors in the indicated direction. If ultimately I is determined to be positive, the actual current in the resistors is in the direction of the arrow. If I turns to be negative, then the current actually flows in the direction opposite to the arrow in the resistors. Similarly, for each source, that is cell or some other source of electric power, the positive and negative electrodes are labeled as well as a directed arrow with symbol for the current flowing through the cell. This arrow tells us that in which direction the current is flowing. This will tell us the potential difference V is equals to V of positive minus V of negative is equals to electromotive force epsilon minus IR, which is our in equation 3.57 between positive terminal and negative terminal, and I here is the current flowing from negative to positive through a cell. If while labeling the current I through the cell one goes from positive to negative, then of course V is equals to E plus I into R, which is our equation 3.79. We get our equation 3.79 if the current is flowing from positive to negative and in the cell. Having clarified labeling, we now state the rule and proof. First rule is junction rule. Means Kirchhoff's rules has two rules. First one is junction rule, in which at any junction the sum of currents entering the junction is equals to sum of currents leaving the junctions. This is a very common or very simple point that we all know that in a junction, if a current is entering from one side of the junction, then the current that is leaving the junction will be equal. This applies equally well if instead of a junction of several lines we consider a point in a line. The proof of this rule follow from the fact that when currents are steady, there is no accumulation of charges at any junction or at any point in a line. Thus, the total current flowing in, which is the rate at which current flows into the junction, must equal to total current flowing out. Means the current that is flowing inside the point must be equal to the current flowing outside from that point. The second rule is the loop rule, according to which the algebraic sum of changes in potential around any closed loop involving resistors and cell in the loop is 0. Means this rule is also obvious since electric potential is dependent on the location of the point. And thus, starting with any point, if we come back to the same point again, then the total change must be 0. In closed loop, we do come back to the starting point, and hence this rule is given to us. You can say figure 3.22 where we have given loops in the circuit. So the loop rule can be clarified from this circuit that when we start from one point, we may come back at another point, and hence the value at that point should be 0. Now let us look at an example 3.6, according to which a battery of 10V and negligible internal resistance is connected across the diagonally opposite corner of a cubical network consisting of 12 resistors, each of resistance 1 ohm, as shown in figure 23. Here we have given a cubical network, and the battery that is used is of 10V, and a negligible internal resistance is connected diagonally opposite the corners, and the network also consists of 12 resistors, and each resistor has value 1 ohm. We have to determine the equivalent resistance of the network and the current along each edge of the cube. So let's look at our solution. According to our solution, the network is not reducible to a simple series and parallel combination of resistors. There is, however, a clear symmetry in problem which we can exploit to obtain equivalent resistance of the whole network. The paths A dash, A, D and AB are obviously symmetrically placed in the whole network. Thus, the current in each must be same, say I. Further, at the corners A dash, B and D, the incoming current I must split equally into two outgoing branches, and in this manner the current in all the 12 edges of the cube are easily written down in terms of I using Kirchhoff's first rule, which was our junction rule, and the symmetry in the problem. Next, take a closed loop, say AB, CC dash, EA, and apply Kirchhoff's second rule, which was the loop rule, as minus IR minus 1 by 2 into IR minus IR plus epsilon, which is equals to 0, where R is resistance of each edge and the epsilon the EMF of the battery, and thus we have EMF E epsilon is equals to 5 by 2 into I into R, and the equivalent resistance Req of the network is Req is equals to E epsilon divided by 3 into I, which is equals to 5 by 6. As we have value of E is equals to 5 by 2, we substituting that value, we get Req, resistance, equivalent resistance Req is equals to 5 by 6 R. For R is equals to 1 ohm, Req is equals to 5 by 6 ohm, and for epsilon is equals to 10V, the current is equals to 3I in the network is 3I is equals to 10V divided by 5 by 6 ohm, which is equals to 12A, that is I equals to 4A, and the current flowing in edge can now be read off from figure 3.23. So this was our solution for example 3.6. Now we will see another example. Our next example is example 3.7. As you can see figure 3.24, we have to determine the current in each branch of the network that is shown in this figure. So let's look at our solution. According to our solution, each branch of the network is assigned an unknown current to be determined by application of Kirchhoff's rule. To reduce the number of unknowns at the outset, the first rule of Kirchhoff's is used at every junction to assign the unknown current in each branch. We then have three unknowns I1, I2 and I3, which can be founded by applying the second rule of Kirchhoff to three different closed loop. In this we have three closed loop and we have to apply Kirchhoff's second rule to these closed loops. Kirchhoff's second rule for the closed loop ADCA gives 10 minus 4 into I1 minus R2, 10 minus 4 into I1 minus I2 plus 2 into I2 plus I3 minus I1 minus whole minus I1, which is equals to 0, which is our equation 3.80a. That is 7I1 minus 6I2 minus 2I3 is equals to 10. By solving the above equation, we get this value. For the second closed loop ABCA, we get 10 minus 4I2 minus 2 into I2 plus I3 whole minus I1, which is equals to 0, and that is I1 plus 6I2 plus 2I3 is equals to 10, which is our equation 3.80b. For closed loop B, C, D, E, B, we get 5 minus 2 into I2 plus I3 minus 2 into I2 plus I3 minus I1 is equals to 0. that is 2i1 minus 4i2 minus 4i3 equals to minus 5, which is our equation 3.80 C. And equations 3.80 A, B and C are three simultaneous equation in three unknowns. This can be solved by the usual method to give i1 is equals to 2.5a, i2 is equals to 5 by 8a and i3 is equals to 7 by 8a. The current in the various branches of networks are A, B proportional to 5 by 8A, C, A proportional to 1 by 2A and D, E, B proportional to 7 by 8A, AD proportional to 7 by 8A, CD proportional to 0A and BC proportional to 2 and half A. It is easily verified that Kirchhoff's second rule applied to remaining closed loops does not provide any additional independent equation. That is, the above values of current satisfy the second rule for each and every closed loop in the network. For example, the total voltage is drop over the closed loop BADEB 5V plus 5 by 8 into 4 into V minus 15 by 8 into 4V is equals to 0 as required by Kirchhoff's second rule. So, this was the solution for our example 3.7. The next topic that we are going to discuss is 3.14 Wheatstone Bridge. As an application of Kirchhoff's rules, consider the circuit that is shown in figure 3.25, which is called the Wheatstone Bridge. The circuit shown in figure 3.25 is our Wheatstone Bridge. The bridge has four resistors R1, R2, R3 and R4. Across one pair of diagonally opposite points A and C in figure, a source is connected. This, that is AC, is called the battery arm. Between the other two vertices B and D, a galvanometer G, which is a device that is used to detect the currents, is connected. Means between two vertices B and D, a galvanometer is connected. This line shows as BD in the figure is called the galvanometer arm. Means the BD line is our arm of the galvanometer G in figure 3.25. For simplicity, we assume that the cell has no internal resistance. In general, there will be the current flowing from all the resistor as well as current Ig through the galvanometer G. Of simple interest is case of balanced bridge where the resistors are such that Ig is equals to 0, means current of galvanometer is equals to 0. We can easily get the balance condition such that there is no current through the galvanometer G. In this case, the Kirchhoff's junction rule applied to the junction D and B shown in the figure immediately gives us the relation I1 is equals to I3 and I2 is equals to I4. And next we apply Kirchhoff's second rule to the both closed loop, which are loop ADBA and loop CDBC. The first loop gives us minus I1R1 plus 0 plus I2R2 equals to 0 as current from galvanometer Ig is 0. So this is our equation 3.81, and the second loop gives upon using I3 is equals to I1 and I4 is equals to I2, I2R4 plus 0 minus I1R3 is equals to 0. This is our equation 3.82. From the equation 3.81, we obtained I1 by I2 is equals to R2 by R1. Whereas equation 3.82, we obtained I1 by I2 is equals to R4 by R3. And hence we obtain the condition R2 by R1 is equals to R4 by R3, which is our equation 3.83a. This last equation relating the four resistors is called the balanced condition for galvanometer to give zero all null deflection. The Wheatstone bridge and its balance condition provide a practical method for determination of an unknown resistance. Let us suppose we have an unknown resistance which we insert in fourth arm R4 is thus not known. Keeping known resistance R1 and R2 in first and second arm of the bridge, we go on varying R3 till galvanometer shows a null deflection. And the bridge then is balanced. For balance condition, the value of unknown resistance R4 is given by R3 and R2 by 1, which is our equation 3.83b. This is the value for our value of unknown resistance R4. A practical device that is using this principle is called meter bridge, and it is discussed in the next section. Now we will look at an example 3.8, according to which the 4 arms of a Wheatstone Bridge shown in figure 3.26 have resistances as AB is equals to 100 ohm, BC is equals to 10 ohm, CD is equals to 5 ohm, and DA is equals to 16 ohm. A galvanometer of 15 ohm resistance is connected across BD. Calculate the current through the galvanometer when a potential difference of 10 V is maintained across AC. Means we have to calculate the current through the galvanometer when potential difference of 10 volt is maintained across AC. So let's look at the solution for this question. According to the solution, considering the mesh BADB, means the loop or say mesh BADB, we have 100 I1 plus 15 Ig, 100 into current of resistor 1 and 15 into current in the galvanometer minus 16 into current I2 is equals to 0, or we can say 20 I1 plus 3 Ig minus 12 I2. We have just uh, solved this above equation and got 20 I1 plus 3 Ig minus 12 I2 equals to 0, which is our equation 3.84a. Now considering the second mesh BCDB, we have 10 into I1 minus Ig minus 15 Ig minus 5 into I2 plus Ig equals to 0, or we can say 10 I1 minus 30 Ig minus 5 I2 equals to 0, or by simplifying this we get 2 I1 minus 6 Ig minus I2 equals to 0. Means we take the factors and simplify the equations, and the equation 2 I1 minus 6 Ig minus I2 is equals to 0 is our equation 3.84b. Now considering the third mesh ADCEA, or a loop ADCEA, we have 60 into I2 plus 5 into I1 plus Ig is equals to 10. So we have 65 I2 plus 5 Ig is equals to 10. How we get 65? We multiplied 5 with I2 and we get 5 I2 plus 5 Ig. And when we add 5 I2 with 60 I2, we get 65 I2 plus 5 Ig is equals to 10. And by simplifying the equation we get, or by factoring the equation, we get 13 I2 plus Ig is equals to 2, which is our equation 3.84c. Now multiplying equation 3.84b by 10 means we multiply this equation 3.84 whole by 10, we get 20 I1 minus 60 Ig minus 10 I2 is equals to 0, which is our equation 3.84d. Now from the equations 3.84d and 3.84a, we have 63 Ig minus 2 I2 is equals to 0, and I2 is equals to 63 Ig divided by 2, which is 31.5 Ig, which is our equation 3.84e. Now substituting the value of I2 in the equation 3.84c, we get 13 into 31.51 Ig plus Ig is equals to 2, which will give 410.5 Ig is equals to 2, and hence we have value of Ig is equals to 4.87 MA. So this is the solution for our example 3.8. Now we will move to our next topic, which is 3.15 meter bridge. So let's start. The meter bridge that is shown in figure 3.27, it consists of wire of a length 1 meter and of uniform cross-sectional area stretched taut and clamped between two thick metallic strips bent at right angles as shown in the figure. The metallic strips has two gaps across which resistors can be connected. Means this metallic strip has two gaps where we can connect resistors. The endpoints where the wire is clamped are connected to a cell through a key. One end of galvanometer is connected to metallic strip midway between two gaps, and the other end of galvanometer is connected to a jockey. The jockey is essentially a metallic rod whose one end has a knife edge which can slide over the wire to make electrical connections. Here R is an unknown resistance whose value we want to determine. It is connected across one of the gaps. Across the other gap, we connect a standard known resistance S. The jockey is connected to some point D on the wire of a distance L centimeter from the end A. The jockey can be moved along the wire. The portion AD of wire has a resistance of R centimeter into L, where R centimeter is the resistance of wire per unit centimeter. And the portion DC of the wire similarly has the resistance R centimeter into 100 minus L. The four arms AB, BC, DA and CD with resistance R, S, RCML and RCM 100 minus L obviously form a Wheatstone bridge, and AC as the battery arm and BD as galvanometer arm. You can see all these things in the figure that I showed you previously. If jockey is moved along the wire, then there will be one position where the galvanometer will show no amount of current. Let the distance of jockey from the end A at the balance point be L is equals to L1. The four resistances of a bridge at balance point then are R, S, RCM L1 and RCM 100 minus L1. And the balance condition equation 3.83a will give us R divided by S. Means here the R is our unknown resistance and S is our known resistance. So R divided by S is equals to R centimeter into L1 divided by R centimeter into 100 minus L1, which is equals to L1 divided by 100 minus L1, and this is our equation 3.85. Thus, once we found out L1, the unknown resistance R is known in terms of the standard known resistance S by R is equals to S into L1 divided by 100 minus L1. Means from equation 3.85, if we want to get the value of unknown resistance R, we can simply move the S from denominator to the right hand side of equation, and when we put it on right hand side it will go in multiplication and we will get R is equals to S into L1 divided by 100 minus L1 as our equation 3.86. Here we got the value of our unknown resistance R. By choosing various values of S, we would get various values of L1 and calculate R each time. An error in the measurement of L1 would naturally result error in the value of unknown resistance R. It can be shown that the percentage error in R can be minimized by adjusting the balance near point, the middle of the bridge, that is when L1 is closed to 15 cm. But this requires a suitable choice for our known resistance S. Now let us look at an example 3.9, according to which in a meter bridge shown in figure 3.27, the null point is found at a distance of 33.7 cm from A. If now a resistance of 12 ohm is connected in a parallel with known resistance S, the null point occurs at 51.9 cm. Then determine the value of R and S. We have to determine the value of known resistance as well as unknown resistance. So let's look at our solution. According to the solution, from the first balance point, we get R by S is equals to 33.7 divided by 66.3, which our equation 3.87. How we get this? We get this from our first balance point. Now, after S is connected in parallel with a resistance of 12 ohm, the resistance across the gap changes from S to SEQ, where EQ is equals to 12S by S plus 12. Now, you arises a question in mind that in our equation 3.87, how we get the value in denominator 66.3S. We get that value because according to our equation of R by S, we have the formula as R by S is equals to L1 by 100 minus L1. Here our L1 value is 33.7. So when in denominator we have 100 minus L1. So when we divide 100 minus 33.7, we get 66.3, and hence we got these values. Now after S is connected in parallel with the resistance of 12 ohm. The resistance across the gap changes from S to SEQ, where SEQ is equals to 12S by S plus 12. And hence, the new balance condition now gives 51.9 by 48.1 is equals to R by SEQ, which is equals to R into S plus 12 divided by 12S. Means when we take SEQ in division, the value on right hand side got flipped on upside down, and hence we got this as our equation 3.88. Now substituting the value of R by S from equation 3.87, we get 51.9 divided by 48.1 is equals to S plus 12 by 12 into 33.7 by 66.3, which gives S is equals to 13.5 ohm. Using the value of R by S above, we get R is equals to 6.86 ohm. Means from the above value, when we solve the equation, we get the value of S as 13.5 ohm and value of R as 6.86 ohm. So this is our solution for example 3.9. Now we will see our next topic, which is topic 3.16, potentiometer. This is our versatile instrument. It is basically a long piece of uniform wire, sometimes a few meters in length, across which a standard cell B is connected. In actual design, the wire is sometimes cut in several pieces, placed side by side and connected at ends by thick metal strip as shown in figure 3.28. In the figure, the wire runs from A to C. The small vertical portions are thick metal strips that connect the various sections of the wire. A current I flows through the wire, which can be varied by a variable resistance, resist, and R in the circuit. Since the wire is uniform, the potential difference between the A point and any point at a distance of L from A is where phi, this symbol is said phi, is the potential drop per unit length. So we get EMF of L length is equals to phi into L, which is our equation 3.89. Now from figure 3.28a shows an application of potentiometer to compare the EMF of two cells of EMF epsilon 1 and epsilon 2. The points that are marked as 1, 2, 3 from a two-way key. Consider first a position of key where 1 and 3 are connected so that the galvanometer is connected to the point epsilon 1 or electromotive force 1. The jockey is moved along the wire till a point N1 at a distance of length L1 from A. There is no deflection in the galvanometer. We can apply Kirchhoff's loops rule to closed loop N1 G3 1A and get phi into L1 plus 0 minus epsilon 1 equals to 0, which is our equation 3.90. And similarly, if another cell EMF epsilon 2 is balanced against L2 into A and 2, we have phi L2 plus 0 minus epsilon 2 is equals to 0, which is our equation 3.91. Now from the last two equations, which are equation 3.90 and 3.91, we can have our equation 3.92 as epsilon 1 equals to L1 by epsilon 2 equals to L2. Means epsilon 1 by epsilon 2 is equals to L1 by L2. This simple mechanism thus allows one to compare the EMF of any two sources, epsilon 1 and epsilon 2. In practice, one of the cell is chosen as standard cell whose EMF is known to high degree of accuracy, and the EMF of other cell is then easily calculated from equation 3.92. We can also use a potentiometer to measure the internal resistance of a cell. You can see figure 3.28b, where we have used a potentiometer to measure the internal resistance of the cell that is connected in the network. For this cell, the EMF whose internal resistance R is to be determined is connected across a resistance box through a key K2. Here in figure you can see a key K2 which is connected to the resistance box as shown in figure. With the key K2, open balance is obtained as length L1, say point A N1. Then the value of EMF is equals to phi into L1, means with the key K2 open. When the key K2 is open, the balance is obtained at a length L1, and then we have the value of epsilon is phi into L1, which is equation 3.93a. When the key K2 is closed, the cell sends a current I through the resistance box R. If V is the terminal potential difference of cell and balance is obtained at length L2, means from point A to N2, then the value of our V will be phi into L2, which is our equation 3.93b. We get this equation in the case when the key K2 is closed. So we have epsilon divided by V is equals to L1 by L2, which is our equation 3.94a, means we have this equation from the value of E by V is equals to L1 plus L2, means value of phi is null. So when we divide E by V, we'll put the value as L1 by L2, means in our equation 3.93a we have value of E is equals to L1, and in our equation 3.93b we have value of E is equals to L2. So we can say that E by V is equals to L1 by L2, which is our equation 3.94a. But epsilon is equals to I into R plus R and V is equals to IR, then this will give us the epsilon by V is equals to R plus R divided by R, which is our equation 3.94b. And from equation 3.94a and 3.94b we have R plus R divided by R is equals to L1 by L2, and hence small r is equals to capital R into L1 by L2 minus 1, which is our equation 3.95. Using the equation 3.95, we can find the internal resistance of given cell, means our equation 3.95 is for finding the internal resistance of a given cell. The potentiometer has advantages that it draws no current from voltage source being measured. As such, it is unaffected by internal resistance of the source, means this advantage is that it will not draw any current from voltage source that is being measured, and such it is unaffected by internal resistance of the source. So this was the advantage of potentiometer. Now we will look at an example 3.10, according to which a resistance of R ohm draws the current from a potentiometer. The potentiometer has total resistance R0 ohm as shown in figure 3.29. A voltage V is supplied to the potentiometer. We have to derive an expression for the voltage across R when the sliding contact is in middle of the potentiometer. So let's look at our solution. According to our solution, when the slide is in middle of the potentiometer, one half of its resistance, means R0 by 2, half of the resistance will be between the points A and point B. Hence the total resistance between A and B, say R1, will be given by the given expression as 1 by R1 is equals to 1 by R plus 1 by R0 by 2, means 1 by half of our resistance, which will give us R1 is equals to R0 into R divided by R0 plus 2R. The total resistance between A and C will be the sum of the resistance between A and B and C, that is R1 plus R0 divided by 2, and therefore the current flowing through the potentiometer will be current I is equals to V divided by R1 plus R0 by 2. As we have from Ohm's law, I is equals to V by R, the current flowing from the potentiometer will be I is equals to V by R1 plus R0 by R2, which will equals to 2V divided by 2R1 plus R0. The voltage V1 taken from the potentiometer will be the product of the current and the resistance R1, which is V is equals to I into R1, and substituting the value for I and R1 we get 2V divided by 2R1 plus R0 into R1, and substituting for R1 we have V1 is equals to 2V divided by 2 into R0 into R divided by R0 plus 2R plus R0 all multiplied by R0 into R divided by R0 plus 2R. which will equal to 2VR divided by 2R plus R0 plus 2R, and we can say V1 is equals to 2VR divided by R0 plus 4R, means 2R plus 2R is 4R. So we get V1 is equals to 2VR divided by R0 plus 4R. So the expression voltage across R when sliding contact in the middle of the potentiometer, it will be 2VR divided by R0 plus 4R, which is our solution for example 3.10. Here we have completed our chapter 3 current electricity. Now we will look at a quick summary. First is current through a given area of conductor is the net charge passing per unit time through the area. Second, to maintain a steady current, we must have a closed circuit in which an external agency moves electric charge from the lower to higher potential energy, and the work done per unit charge by the source is taking the charge from lower to higher potential. Every energy that is from one terminal of the source to other terminal is called electromotive force or EMF of the source. Note that the EMF is not a force, it is the voltage difference between two terminals of a source in an open circuit. Third is Ohm's law. The electric current I flowing through a substance is proportional to the voltage across its end. That is, V is proportional to I, or V is equals to R into I, where R is called the resistance of the substance. The unit of resistance is ohm. 1 ohm is equals to 1 VA inverse. The fourth is the resistance R of a conductor depends on the length L and cross-sectional area A through the relation where P is called the resistivity, is a property of material and depends on the temperature and pressure. We can say resistance R is equals to resistivity into the length L divided by cross-sectional area. Fifth is electrical resistivity of a substance varies over a very wide range. Metal have low resistivity in the range of 10 raised to minus 8 ohm meter to 10 raised to minus 6 ohm meter. Insulators like glass and rubber have 10 raised to 22 to 10 raised to 24 times greater resistivity than the metals. Semiconductors like Si and Ge lie roughly in the middle range of resistivity on a logarithmic scale. 6. In most of the substances, the carriers of the current are electrons. In some cases, for example, ionic crystals and electrolytic liquids, positive and negative ions carry the electric current. 7. Current density J gives the amount of charge that is flowing per second per unit area normal to the flow. J is equals to NQVD, where N is the number of density, number per unit volume of the charge carries each of the charge Q of charge carriers, each of charge Q, and the VD is drift velocity of the charge carriers. For electrons, Q is equals to minus E. If J is normal to cross-sectional area A and is constant over the area, the magnitude of current I through the area is NEVD into A. H is using E is equals to V by L, I is equals to NEVD into A, and Ohm's law one can obtain small e into capital E into E divided by M, which is equals to the resistivity into N square divided by M into Vd. The proportionality between the force E into E on the electrons is a metal due to the external field E and the drift velocity Vd, not acceleration, can be understood if we assume that the electrons suffer collisions with ions in metal which deflect them randomly. If such collisions occur on average at a time interval t, Vd drift velocity is equals to A into the average time interval equals to E into time interval divided by M, where A is the acceleration of the electron. This gives us the resistivity P is equals to M divided by N square into the time interval t. 9. In the temperature range in which resistivity nearly increases linearly, the resistivity which increases linearly with the temperature, The temperature coefficient of resistivity alpha is defined as fractional increase in the resistivity per unit increase in the temperature. 10, which is Ohm's law, is obeyed by many substances, but it is not a fundamental law of nature. It fails if A. V depends on I non-linearly. B. The relation between V and I depends on the sign of V from for the same absolute value of V. C. The relation between V and I is non-unique. An example of A is when the resistivity increases with I even if temperature is kept fixed. A rectifier combines feature A and B. Gas GAAS shows the feature C. So this A, B and C three cases where the Ohm's law may fail. 11. When a source of EMF epsilon is connected to an internal resistance R, the voltage Vext across the R is given by Vxt is equals to I into R, which is equals to epsilon divided by R plus R whole into R. 12. A total resistance R of resistors is connected in series is given by R is equals to R1 plus R2 plus up to Rn, and the total resistance R of n resistors connected in parallel is given by 1 by R is equals to 1 by R1 plus 1 by R2 plus up to 1 by Rn. 13. Kirchhoff's rules. First rule is junction rule. At any junction of circuit elements, the sum of the current entering the junction must be equal to the sum of current leaving the junction. And second rule is loop rule, according to which the algebraic sum of changes in potential around any closed loop must be 0. 14. The Wheatstone Bridge is an arrangement of four resistances R1, R2, R3 and R4 as shown in the text. The null point condition is given by R1 by R2 equals to R3 by R4. 15. The potentiometer is a device to compare potential differences. Since the method involves a condition of no current flow, the device can be used to measure potential difference, internal resistance of a cell and compare EMFs, electromotive forces of two sources. So this was our quick summary. Here we have ended our chapter 3 current electricity. We will start our chapter 4 from the next session. Thank you.